Have you ever really stopped and thought about it? I mean, every time you send a text, stream a movie, or just hop on Wi-Fi, you're using something that feels, well, kind of like magic. But it's not. It's physics. And in this explainer, we're going to pull back the curtain and see exactly how it all works. So let's just jump right in with the big question. How on earth does a signal, a piece of information, get from a cell tower to your phone, or from your router to your laptop, when there's nothing but air in between? To get to the bottom of that, we actually have to travel back in time, to the 19th century, when scientists were scratching their heads over two very mysterious and what they thought were two very separate forces. Okay, so try to picture the world back then. Physicists were studying electricity on one hand and magnetism on the other. And to them, these things were totally different. They each had their own set of rules, and they seemed to exist in their own separate universes. But what's so wild is how similar they looked on paper. Electricity had its positive and negative charges. Magnetism had its north and south poles. And in both cases, opposites attracted and likes repelled. Scientists had this phrase for it: action at a distance, because, one magnet could push another without ever touching it. The rules were almost identical, but for a long time, everybody was convinced they were just two completely different phenomena. Now, to explain that action at a distance weirdness, this brilliant thinker, Michael Faraday, he came up with the idea of a field. He imagined that a charge doesn't just sit there, it actually fills the space all around it with this invisible influence, an electric field. So when you bring another charge close, it's not feeling the first charge directly. Nope, it's feeling the field that the first charge created. And that was a huge, huge mental leap. So for a long, long time, these two forces were studied side by side, but never together. But then, a few discoveries started to pop up, and they began to show a little crack in the wall separating electricity and magnetism, hinting that maybe, just maybe, there was a deep connection hiding there. And this was the first bombshell. Someone figured out that if you run an electric current through a wire, which is really just a bunch of charges on the move, it creates a magnetic field around that wire. You could literally hold a compass next to it and the needle would swing like crazy. It was proof. Electricity in motion could actually make magnetism. The two separate worlds were suddenly starting to overlap. This is where our guy Michael Faraday comes back into the picture. He started wondering, okay, if a moving charge creates a magnetic field, could it work the other way? Could a magnetic field somehow create a current? And he discovered that yes, it could. But, and this is the crucial part, the magnet couldn't just sit there. The magnetic field had to be changing. If you moved a magnet back and forth near a coil of wire, a current would start to flow, like magic. No battery needed. This incredible relationship got its own name, Faraday's law of induction. All it's really saying is that a changing magnetic field creates an electric field, which then pushes charges along to make a current. Now, this isn't just some neat party trick. This is the principle behind every single power plant on Earth. It proved the connection wasn't just a one-way thing. It was a two-way street. All right, so we've got these two amazing connections. Moving electricity makes magnetism, and changing magnetism makes electricity. But all the puzzle pieces were still kind of scattered on the table. It took a Scottish physicist, a genius named James Clerk Maxwell, to finally see the whole picture and put it all together. And look, you don't have to take my word for how important this guy was. Albert Einstein himself said, "One scientific epoch ended, and another began with James Clerk Maxwell." So yeah, this was a pretty big deal. He didn't just add a new idea. He completely changed the game. So what Maxwell did was he took everything they knew about electricity and magnetism and boiled it all down into just 4 beautiful equations. But he also added one final critical piece to the puzzle. He proposed that if a changing magnetic field creates an electric field, then a changing electric field must also create a magnetic field. It created this perfect, elegant symmetry. And with that, they weren't two forces anymore. They were one, electromagnetism. And this is where the theory goes from being really clever to being absolutely mind-blowing. Think about it. If a changing electric field creates a magnetic field, and that changing magnetic field then creates a new electric field, what happens? Well, Maxwell realized they would just create each other over and over and over again in this endless dance that would travel through empty space as a wave. So, using only his 4 equations, Maxwell decided to calculate the speed of this theoretical wave. He plugged in the numbers for electricity and magnetism, did the math, and out popped this number, 300 million meters per second. Now, for any physicist living at that time, that number wasn't just some random speed. It was instantly recognizable. They knew that number. It was the speed of light. In one of the most incredible aha moments in all of science, Maxwell had just proved, with pure math, that light itself is an electromagnetic wave. This was it, the grand unification. So, with this unbelievable new understanding of the universe, what did humanity do? Well, we basically built the entire modern world with it. Let's trace the path from these equations on a page to the device you're probably holding in your hand right now. You can literally draw a straight line. In 1831, Faraday's discovery gives us electric generators. Then, in 1865, Maxwell's theory tells us that there must be other invisible electromagnetic waves out there, not just light. A couple decades later, Heinrich Hertz actually builds a machine that creates and detects these waves, radio waves, proving Maxwell was right. And from there, it's a direct shot to radio, TV, Wi-Fi, cell phones, all of it. So when you boil it all down, it's pretty simple. Our modern life runs on these 2 massive breakthroughs. Faraday's law of induction is the reason we have electricity to power everything, and Maxwell's waves are the invisible roads that carry all of our information through the air. Which brings us right back to where we started. That signal hitting your phone, it's not magic at all. It's an electromagnetic wave, oscillating at a very specific frequency. It is the direct, tangible result of a 19th century quest to understand a couple of invisible forces. You know, the story of Faraday and Maxwell is just such a powerful reminder. It shows that sometimes the most abstract, fundamental questions about how the universe works can lead to the most incredible technological revolutions. It really makes you wonder, doesn't it? What are the modern-day versions of electricity and magnetism? You know, the things that seem totally separate right now, but might just be 2 sides of a much deeper, undiscovered coin. What fundamental discoveries being made today will end up building the world of tomorrow? It's a pretty cool thing to think about.